Hello, you beautiful people. So today is the solution of worksheet number 5. It was about the Recycle-Reactor. And there you had some questions. So we had the reaction that you already know from the continuously stirred tank reactor and the plug flow reactor. So A reacts to half B and C. It's a very simple first order reaction, so it's just the rate constant times the concentration of A. And to make it even more easier, it's just 1 for the rate constant. We have a change in density, so this can be taken into account by epsilon of plus 0.5. And now we are looking at a recycle reactor. This means that a part of your volume flow from the outlet of your reactor is recycled back to the inlet of the reactor. And yeah, what was given, we have a starting concentration of 20 kilomoles per cubic meter, and we want to achieve a conversion of 80%, and we want to produce a mole flow of component C of 30 kilomoles per hour. And since you know this already here, the inlet concentration for C and B is 0, and yeah. What was your task? The task was determine the inlet concentration Ca in and the inlet conversion Xa in. Then you had to do a graphical sizing of the reactor, and then you have to do it analytically by solving integrals, and part D was using the Euler scheme, so which could be done by MATLAB. Okay, let's have a look. So first part was determine the inlet concentration and the inlet conversion. So here you can see our reactor again, and what we want to know here is the inlet conversion and the inlet concentration, and for this I gave you some formulas in the script. So basically it's just putting in the values that we had here. So let's try this. Oh, it's not laser pointer, it should be smart pen. Okay, so starting concentration Ca in is so this is first. Starting concentration 20 kilomoles per cubic meter times, and then it's 1 plus R. R was 5. We have a recycle ratio of 5. So this means that the outlet volume flow is V dot, and here you have 5 times the outlet volume flow is recycled back to the reactor inlet. So times 1 minus 0.8. So we had this at the outlet concentration, so this should be 0.8. And we have to divide this by 1 plus 5, 1. Whoops, yeah, minus is okay. Then we have epsilon was 0.5, and our conversion was 0.8 again. 0.8. Okay. Then 20 kilomoles per cubic meters. Then let's have a look. 1 minus 0.8 is 0.2, times 5 is 1. So this means we have 2. 2, and 1.5 times 1.8 is 1.4. It's 0.4 plus 1 is 1.4, and times 5 should be 7, and plus 1 it should be 8. So this is the same as 1/4, and if you divide it, then you end up with 5 kilomoles per cubic meter. Okay, and the inlet conversion, this is quite easy. Xa in is just R over R plus 1 times Xa. The outlet conversion, so 5 over 6. 5 over 6 times 0.8, and then you end up with 0.667. Okay. This should be the values. I think a lot of you had this. So for part B, somehow this was more difficult, but we will have a look. Okay, B was plot the 1 over R, the XA diagram, determine the required volume of the Recycle-Reactor using this diagram. And then I put here the formula that you need, that you can use for this task. But let me start with a small repetition of how to get this graph here. So this was creation of the 1 over R XA diagram. Oh, this should be small. Okay. Yeah, the reaction rate. Reaction rate is just K times CA. And yeah, what was about CA? I put this, whoops, here on the, where there I put it. Okay, here you can see how our concentration depends on the starting, on the inlet concentration and on our conversion. So we just have to put in these correlations. So this is our starting concentration times 1 minus XA over 1 plus epsilon XA. So let me, as an example, XA, let's calculate the reaction rate for a conversion of 70%. So then we have R is, K is 1 hour to the power of minus 1 times 20 kilomole per cubic meter times 1 minus 0.7 is 0.3, and below it you have 1 plus 0.5 times 0.7, and if you calculate it, then you get 4.44 kilomoles per cubic meter and hour. And for the graph we need 1 over R, so we just have to invert this value, and then our new value is 0.225 cubic meter hour kilomole. Okay, and if you want to have this as a full formula, then you just have to convert then you just say, okay, I want to know the analytical expression for 1 over R. This is just the same as 1 over KCA, and you just have to invert this. So it's 1 plus epsilon XA over KCA0 times 1 minus XA. Okay, so, and if you plot this expression, then you end up with this line here. So basically this is 1 over R is 1 CA0, 1 minus 1 plus epsilon XA, 1 minus XA. Hopefully. Yes. This should look fine. And if you compare it here, we just calculated a value of, for a conversion of 70%, we calculated a value of 0.225, and this fits very well here in this diagram. So basically we did something right. Okay, this is how you construct, this is how you construct this curve. And now we need to evaluate this integral here. And for this, so we have to integrate from our inlet concentration. This was about something here, 0.667, and our outlet conversion is 80%. So this is this value here, and I put it here. So I highlighted it here. Okay, it's not fitting very well. Let's do it like this. Okay. So, and what we need here is now we have to integrate 1 over r with respect to the conversion. So this means we wrong direction, this one. Okay, this means we need to evaluate this area here. And so if you want to do it in a very simple way, then you just say, okay, I need something like a rectangle that has the same size as this area here, and maybe assume something like this rectangle here, and this should be, so I just said, okay, this might be equal to 0.27. Okay, and so now our tau. So we are just using the formula. Tau is equal to our starting concentration, 20 kilomoles per cubic meters, times r is 5, so r plus 1 is 6 times 6, and then we need to have the integral here. So this part is the same as this green area here. So, and the green area is just the height of the rectangle. Now I miss out my units. Okay, I put it here. Cubic meter hour over kilomoles. And then we also need our dxa. We need the length of at our x-axis here. So this is times 0.8 minus 0.667. So it's conversion, so it's dimensionless, no problem. Okay, and if we now calculate this, then we find out that our tau is the same as, where is it? 4.309 hours. Okay. Another way of doing this is put it in next color. You can also say, okay, what does it mean here? This r plus 1 is 6, and if we multiply this area here by 6, then it's the same amount area as this. So if you So from my perspective, it's even more easier to calculate it like this. So then your residence time tau is the same as your starting concentration, kilomoles per cubic meters. And now this big area is the whole part here, and here you just have to multiply it with the height of the rectangle. This is 2.7 cubic meter hour per kilomole times the whole length of the x-axis, so it's 0.8. And if you calculate it, then of course it should be the same result, so it's 4.309 hours. So there are two ways how you can interpret this this solution. Okay, and actually it wasn't asked for the residence time, but it was asked for the volume of the reactor, and the volume is just your residence time times the volume flow. This is 4.309 hours. The volume flow we had in the last worksheet, this was 0.875 cubic meters per hour. Then you end up with the volume of 8.08 cubic meters. Okay. Now, it's on the next slide. Okay. The next one was calculate the volume V by solving the integral of equation 8. A table of integrals can be found here. Compare it to your graphical solution. Okay, what we need to do now is we have to insert here the expression for our 1 over r. So 1 over r, this was the same as k CA0, and then we have x plus epsilon xa 1 minus xa. And you have to solve this integral. So we don't need to do everything from scratch. Maybe you remember worksheet number 4. So this was the worksheet that you did the last time, and there we had something like this. We looked it up in the table of integrals, and there you had a quite similar expression, but if you compare it, you have here, so our tau for this was the reaction for the PFR. If you have a pure plug flow reactor, then you just have your inlet concentration here, and here we have our inlet concentration times R plus 1. And the other thing is that our integral for the plug flow reactor starts at 0, or here 0, but for our case we are integrating from the inlet conversion to the outlet conversion. So basically we can use the results that we found last time, but just with a very small modification. So what do we need to do? We have to say, okay, here we have to add R plus 1, and here we have to do it's not xa, but it's the lower integration bound is R over R plus 1 times xa. So this was 0.667, and this was 0.8. Okay, and now we just have to put it in, so we can rewrite it. So we can do some more simplifications. Tau is 1 over k R plus 1, and then it's minus epsilon xa minus 1 plus epsilon ln 1 minus xa, and this should be in the range, where do I put it, 0.667 and 0.8. Okay, and then if you calculate it, then you end up with, let me see, so this is 1 over k times 6, and then to give you some intermediate results, for the first term I get 2.014 minus 1.316, and then I have a residence time of 4.188 hours. If you compare it with the results that we had from the graphical interpretation, this was 4.3, and the correct value is roughly 4.2, so the graphical result is not that bad. Okay, and then we need to calculate the reactor volume. So V, the volume, is the residence time times the volume flow, 4.188 hours times 1.875 cubic meters per hour, and then you get a reactor size of 7.85 cubic meters. So this is exact, and graphical we had 8.0 8 graphical solution. So let's say it's a reasonably good result. So roughly 7.8 compared to 8.1, so it's okay. But maybe if you look again here at your graphical, maybe you could say, okay, it's not 2.7, but it should be something like 2.65, I don't know. Okay, then the last part, determine the required reaction volume, VSIM, by a numerical simulation, the Euler scheme including the effect of changing density, and compare it to the volume of part C. I will show you a new video to not so to make sure that it's not too long here, but I just want to give you the main part of the code I want to show you already here. So basically I programmed two times the solution, and maybe this one here is more easier to understand, I hope. So basically this is the numerical calculation for a simple plug flow reactor, and the only thing that we have to look at is this correction here for the volume flow. So in this approach here, you have your inlet volume flow is corrected by R plus 1. This is one special thing, and we have our conversion here is also somehow corrected with the recycle ratio. So the other things here, so this is just you calculate your concentrations by just dividing the mole flow by the volume flow. Then you calculate your reaction rate. Then using the reaction rate you can calculate your change in the mole flows, and with the change in the mole flows you can update your mole flows, and basically that's it. And then it's next cycle. So you should know this from the plug flow reactor. And two things we have to talk about is the correction of the volume flow and the correction of the conversion. But this I will show you in the next video. Thank you for watching.